continue talk about frequency response function in motor coordinates. The blue color here is from E1 tilt to Q1. So the transfer function you have to be aware of that the differences between this and the transfer function we talked about it last week. The blue color there, we have two frequency response function in here. One is from U1 tilt to Q1. So that's G1 tilt omega. And G2 tilt omega is really from U2 tilt to Q2. So this is different from the one we talk about from U1 to W1 and from U. So that we have, last week we have U1 to W1, let me right here. Last week we have G11 omega is from U1 to W1. And then we have G21 omega is from U1 to W2, right? We have G12 omega is from U2. Am I doing right? Yeah, I think so. U2 to W1. Then we have G22 omega is from U2 to W2, right? So we have basically four different frequency response functions. If we use the physical coordinate U1, W1, U1, W2, U2, W1, U2, W2, however, G21 and G12, they are identical. Okay? But now, here, we transform this frequency response function into the motor coordinates. If into the motor coordinates, you have only two frequency response functions. That means U1 tilt to UQ1, U2 tilt to Q2 because they are not coupled. There's no such U1 tilt to Q2, no. I understand now? So, if you did the motor coordinate, this is in the physical coordinates. Okay, this is in the motor coordinate. This is in the motor coordinate. So, in the physical coordinate, then we have G11, G21, G12, G22. In the motor coordinate, we have the G1 and the G2. The input U1 tilt, U2 tilt. This U1 tilt is U1 plus U2. U2 tilt is U1 plus and U1 minus U2, right? So that's the differences. Now the question is, we have these two frequency response functions in motor coordinate. Can we go back to solve our physical coordinate like that? And the answer is of course yes. But if you look at the frequency response function in the motor coordinate, it's much simpler form and much easier form to see. But sometimes we don't want to look at only this kind of the motor coordinate frequency response functions. And your phase angle, the same thing. Your phase angle is, see, at the pole, the phase can be from 0 becomes to minus 180 degrees, and another is the same thing. Okay, that's in the for each input-output pair in the motor coordinate. So in the motor coordinate, in the physical coordinate, they look different, but they are doing the same. They are exactly the same thing. If we want to transform from motor coordinate to the physical coordinate, and this is the transformation. We have a transformation times diagonal G1 tilt, G2 tilt, because those are all diagonal. is from, that's because from U1 tier to Q1 and U2 tier to Q2. There's no U1 tier to Q2, no U2 tier to Q1. So those are the differences. And this, the transform function, the K3 is 1 over square root, because that's just a transpose. And if you do that, then you will get identical, the same as your original physical coordinates if you do this. In other words, if you G omega, you from G tilt, G1 tilt and G2 tilt, you do this just like mass matrix transformations. You have the script T times this and script T transpose. And this comes from those model coordinate transformation, right? Formulations. And that's, okay, now, you have any questions? This just gives you some idea how you use the model coordinates, how you use the physical coordinates, and also gives you the idea of what is the differences between the physical coordinate and model coordinates. Any questions? No? Okay, good. All right. All right, and this just gives you overall pictures. On the left hand side, then you have the model coordinate. On the right hand side, you have physical coordinate, and how they look different, but they represent the same input and output. If you look at from the physical coordinate E1 to W1, E1 to W2, U2 to W1, U2 to W2, and this is how it looks like it. And so, in many cases, in controller design, sometimes we look at this kind of the model coordinate frequency response function too, because that's much cleaner and it's easier to understand what's going on. Okay. I'm going to move this to called multiple spring system, and I will tell you that how can you assume you have an infinitive number of springs? Then, if you have infinitive number of springs, then you will be able to write a partial differential equation to represent the system rather than an ordinary differential equation. How can you do that? This is the way we do. The Newton law, if you look at this multiple spring system from the Newton law, and again, this W1, W2, W3, W4, they are absolute displacement. Because they are absolute displacement, it's easy to write this differential equation, and if n can be 1,000, can be 10,000, can be 100,000, and if you model a aircraft, if you model a Boeing 747, if you go to Boeing company and then you ask them how you model your 747, how many degree freedoms you model it, they will show you the mass matrix may be 10,000 by 10,000. All right, and they show you the stiffness matrix may be another 10,000 by 10,000. So they have 10,000 degree freedoms. Say, oh yeah, my aircraft 747 has 10,000 frequencies. Do you really believe there are 10,000 frequencies? The answer is no. If you fly in the air, the XI may be maximum one. How many frequencies you can be excited? Any guess? Huh? Maybe only pretty few, less than 10. No. After they model it, they write the mass matrix like what I did for you, the mass matrix, they write the stiffness matrix, and they solve these frequencies. Then they go to their laboratory, their wind tunnel to test it. And they will find out, oh yeah, these are frequencies. My theory, the frequencies is 1 hertz. My experiment is 1.5 hertz. They will simply say that's close enough. You know, 1 hertz and 1.5 hertz, 50% off, but they will tell you that's good enough. Because it's very difficult to model it, to model any very complex structure, like an aircraft. It's not easy to model it because you have so many nails, so many screws, so many different components, and they have a chair, they have tables and everything there. It's difficult to model it. It's exactly the same as you're testing inside here. Because some workers may not tight enough the screw, all right, and that affect frequencies too. So that's many cases for a system like 101. You might be able to represent that 101 just by 1 BDE rather than 10,000 degree freedoms. Sometimes people like to do that. So I'm going to show you that if you have a 10,000 degree freedoms like this, multiple splitting frequencies, maybe I can just use another form of the differential equation to represent it. All right, so this is the way we do. All right, now if you have a Newton law, second law, the matrix equation like this, okay, that's the matrix equations. You can see that if you use the absolute displacement, your mass matrix likely to be just diagonal. And your K matrix will be coupled like this. This is the K matrix. Most of them are still zeros. Only the elements next to the diagonal elements, they have values. So you call banded stiffness matrix. The banded. It's stiffness matrix is banded. So if you look carefully here, the stiffness matrix